Okay, so it's the 28th of June today, which is 6:28 for I think people that live in America. Anyway, that's important because 6.28 is tau, which is twice as big as pi, or at least approximately twice as big as pi, which is important because a lot of people propose a better circle constant than pi, which instead of being based on the ratio between the circumference and the diameter, is actually based on the circumference and the radius, hence tau 6.28 something. So in honour of Tau Day, I'm going to criticise the Pi manifesto. I'm going to try and refute it, and the Pi manifesto is here, and they're trying to defend the concept of pi over tau, why actually pi is a superior circle constant to tau. Now, I'm going to refute all these points. There's 8 points essentially. I'm going to try and refute all of them. So here we go. Okay, so the first defence is that the circle constant pi, which is based on the diameter, is better because the diameter is easier to measure in a circle than the radius. And this is true mostly because it's very difficult to know exactly where the centre of a circle is. However, the measurement really isn't that important. What's important is the mathematical elegance of the definition. And a circle can be very easily defined in terms of its radius. So we simply have the centre point here, and we can define a circle as being the locus of all points that are equidistant from this point. So all these points here, the thing that they have in common is that they're all the same distance from the centre point. And the distance that they are from that centre point is defined as the radius. So any circle at all in 2D space can be parameterized in terms of the centre point, the x and y coordinates of the centre, and its radius, and that's very simple definition. Now let's try to do the same with the diameter. Well, here's a point, this is a diameter. Well, I suppose a circle has an arc that goes like that, but that's not very mathematically rigorous. I mean, you probably could define it using the diameter, but it would be a lot more difficult to do. Whereas with the radius, it's very straightforward. So there's a natural elegance with defining a circle in terms of its radius. And mathematicians acknowledge this anyway. That's why we measure angles in radians. We don't measure them in diameters. So this is already acknowledged. Now, the Pi manifesto then goes on to talk about the area of a circle. So they kind of almost acknowledge that, well, the circumference of a circle defined by pi times the diameter is less elegant than the circumference of a circle defined by tau times the radius. Or, again, as a lot of people say, it's 2 times pi times the radius, so you have that unfortunate 2 in there, makes it less elegant. So the Pi manifesto almost acknowledges that. But then they go on to say, well, actually, the area of a circle is more elegant because there's no factor of 2 there. And with the tau, you would have a factor of 2 with tau. But that, again, that's not quite true because for 2 reasons. Firstly, you can see that this is only the case if we define it in terms of the area in terms of the radius anyway. So we have pi r squared, but in reality it should be pi d squared over 4, which is really not elegant after all, because of course pi is defined in terms of the diameter. So we're kind of mixing notations here in a way. And secondly, this half that actually does appear in the half tau r squared is quite a useful half because it gives a hint about how the equation is derived, how the area of a circle is derived. So here's sort of a brief proof of the area of a circle, and this half comes from an infinitesimal triangle which I'm integrating over the whole circle. And of course we know that the area of a triangle is a half times base times height. So that's kind of where the half comes from. So we see this quite nice link between triangles and circles using tau that we don't see with pi. So that's quite a nice half. It's not like the half from the circumference 2 pi r, which the 2 is completely arbitrary in the definition of circumference, whereas this half at least can be justified in terms of where it comes from. But in any case, we're having to use the radius anyway. So this is only elegant because we're using the radius of the circle, which more naturally goes with the tau constant anyway. So the only reason that this looks elegant is because you're mixing the notations in a way. So it's not really elegant at all. So the Pi manifesto goes on to continue to talk about areas of a circle, and they say, well, here's a circle. Let's say we've got a quarter of the circle, and it's a unit circle, so it has a radius of 1. Well, this has the area of pi over 4, and it's a quarter of a circle. Isn't that elegant? It's better than saying tau over 8. Well, maybe, but again, this only applies because we're defining the unit circle in terms of its radius. We're defining a circle in terms of a radius of 1. But if you're using pi, then surely you should be defining a unit circle in terms of a diameter of 1, not in terms of a radius of 1. And so again, we end up with this clunky formula in terms of pi d squared over 4, which would then imply that if you're defining a unit circle in terms of a diameter of 1, then this is actually pi over 16, not pi over 4. And I think the factor of 2 becomes less of a problem then than this factor of 4. So the tau, once again, is more elegant in terms of areas of a circle than the pi anyway. Okay, so the next one the Pi manifesto goes on about is it goes into some slightly more complicated mathematics and talks about the Gaussian distribution, which is this sort of nice bell curve. And if you integrate over the whole distribution, you get the square root of pi. And they would argue that, well, that's a lot more elegant than the square root of tau over 2. Which, okay, it's true, you have this unfortunate 2 here. But this 2 really isn't that unfortunate, because again, there's a very clear mathematical reason for this 2. I mean, I've written this quick proof of the Gaussian distribution, and it comes from integrating e to the minus r squared times r, and the factor of 2 kind of falls out from that integration. So again, this factor of 2, it represents something. It's not completely arbitrary, and it gives you a hint about how you might go about deriving the equation. I mean, I'm not saying this is not easy to derive if you've never seen it before, and I certainly couldn't have done it if I'd never seen it before, but I think I would have a better chance of being able to reverse engineer this if I just saw the square root of tau over 2 than if I just saw the square root of pi, because the half factor there kind of gives you at least a hint that you might be having to do some integration to get that factor of a half. Okay, it's a long shot, but anyway, at least this half isn't arbitrary. Okay, so the next one after that is talking about the sum of interior angles, always sum in a triangle sums to pi, and then you can represent it in other polygons in terms of pi as well. And again, this is true, but I mean, we're talking about internal angles. Let's talk about external angles. The sum of any external angles in a polygon makes tau, which intuitively is almost obvious, because if you look at the external angle, so you're stood here, you kind of do 120 degrees to get to here, do a third of a circle, tau over 3, another tau over 3 to get to here, another tau over 3 to get to here. So you're doing a complete tau around the polygon. Now, you can kind of prove, at least for regular polygons, quite easily what the sum of internal angles are, just by sort of acknowledging that, well, you've got a line here, so that's going to be tau over 2, which is kind of here. So tau over 2 minus your external angle, so it's regular. So let's say for a triangle it's going to be divided by 3, but in an n-sided polygon it's going to be divided by n. So the whole thing divided by n here. So we've got tau over 2 minus tau over n to get 1 of these angles, and then multiply again by the number of sides. Sorry, these should both be k. I've sort of mixed notation here, but anyway, the point is the tau over 2 minus tau over k multiplied by k, and then you can simplify that to tau k over 2 minus 1 for the general formula. And this also applies to irregular polygons as well, but that's more difficult to prove. So again, the point I'm making here is that this formula is not as nice as the one involving pi, but it comes from a good place. It comes from an easier to prove place. So you kind of understand where these formulas are coming from. Whereas with pi, again, it just seems a little bit arbitrary. So anyway, the sum of external angles always makes tau. So there you go. So let's go on to number 6. They talk a little bit about trig functions, and this one isn't really. I wouldn't even argue this is a particularly good defense of pi. I mean, it's not really defense at all. They just argue that some trig functions They seem to be responding to a rebuttal more than anything else. They just argue that some trig functions have a periodicity of pi rather than tau. Again, that's true, but the most fundamental trig function of all, the sine function, or cosine function depending on your mood, has a periodicity of tau, not pi, or 2 pi. So it has a periodicity of 2 pi or tau, and these are the most fundamental trig functions to begin with. The function tan, which is defined as the sine divided by the cosine, has a periodicity of pi, but this is not really the most fundamental trig function. In any case, you can kind of justify why that has a periodicity of only half a circle versus a full circle. So let's have a look at how the tan function is defined. It's defined as the so let's say we have a point on the circle that's moving around, maybe in this anti-clockwise direction. Tan would maybe be defined as the ratio between this vertical side of the triangle and this horizontal side, and you can kind of see that when you're in this first quadrant, you're going to get a positive value divided by a positive value. Then when you're in the second one, you're going to get a negative x divided by a positive y, so you're going to get a negative value here. But then when you go into this quadrant of the circle, you're going to get a negative divided by a negative, and they're kind of symmetrical. So a negative divided by a negative is a positive. So this half of the circle is going to repeat exactly the same as what you got in the first half. So that's kind of acknowledging that. And the tau over 2, that the fact that you're dividing by 2 kind of acknowledges that the periodicity only lasts in half of the circle, and this is the reason why. So again, it's kind of more intuitive, but the most fundamental trig functions have a periodicity of tau anyway. Number 7 just goes through a whole bunch of mathematical formula that use pi instead of tau, and they have less of these constants like 2 or half or whatever with pi, that work better with pi as opposed to tau. Now, the thing is, these are just cherry picked. Of course, there are lots of formula where the opposite is true, where tau works better than pi. And in fact, in physics, for example, there's something called the Dirac constant, which is Planck's constant divided by 2 pi, or divided by tau, and it's used so much that it has its own special letter, which is like a h with a bar through it, which is Planck's constant divided by tau. So in physics, you at least in this case, you divide by tau all the time, as opposed to pi. And again, you do that in a lot of mathematical equations as well. But you can always cherry pick some of the better equations that work better with pi and some of the ones that work better with tau. But in the end, there are lots of each. But I would argue that in the case of tau, they're more intuitive than they are with pi. Number 8 is the Euler identity, and this one they're very, very wrong, I think. They're trying to argue it's more elegant when you use pi, and this is definitely not the case. When you use tau, you get this sort of lovely identity that e to the I tau is equal to 1. And this is we're thinking in the complex plane, complex numbers, which is sort of like 2-dimensional numbers, where you have the real axis, which is just 1, 2, 3, 4, normal numbers. But then on the other axis, you have these imaginary numbers, which are like multiples of the square root of -1. So it's sort of 2-dimensional numbers, you can think of them. Now, if you use pi, you get e to the I pi is equal to -1, whereas if you use tau, you get e to the I tau is equal to +1. Now, the nice thing about using tau is that it demonstrates the periodicity of this function much better. And you can see here I put this n, and n can be any integer. So e to the 2i tau, e to the 3i tau, e to the 4i tau, they all equal 1. And again, another way you can think about it is that if you have e to the I theta, and theta is like an angle in this complex plane, this 2-dimensional plane, that is equal to e to the I theta plus n, which again n is an integer, times tau, and n can be any integer. So tau really nicely demonstrates its periodicity in a way that pi doesn't, because pi is sort of half a circle away from 1 in the complex plane, whereas e to the I tau is a full circle away from 1 in the complex plane, and it also equals 1 because once you're a full circle back, you get to where you started with. So with the Euler identity, it's much better to use tau. rather than pi, it's a lot more intuitive. And again, the reason it's a lot more intuitive is because, I mean, this circle constant, they're all about circles, right? So when you're looking about the complex plane, again, you're coming across something that resembles a circle in the complex plane. So there you go. I would say that it's not just about which formula is more simplistic looking, although again I think tau would still win on this basis, but it's more about which is more intuitive. Now, in terms of the way it's defined, tau is definitely more intuitive, but also even in some of these more complicated formulas, with tau you can see where these factors of 2.5, if they do appear, come from. Whereas when you're looking with pi, these factors of 2.5, they're less intuitive. So I'll definitely say that even though pi does simplify some formula, it simplifies the formula that you might not want to simplify, in the sense that those factors of 2.5, etc. can actually be quite useful. So this is my defense of tau on tau day. Tau is definitely less arbitrary and a lot more elegant than pi. It's definitely the circle constant of choice.